If you've ever been to a Starbucks, then you've probably experienced the joy of wireless. You may have a laptop or a personal smartphone or something like that, and it just connects almost magically to the internet without wires, without mess, and without fuss. It's a great type of an environment. It also used to be that when you wanted to set up a network in your home, you had to run cables, which meant you had to put holes in the wall, you had to put outlets in. It could be very cumbersome and time-consuming. With wireless, you simply buy a wireless router or access point, you get client devices in your computers, and you can have it up and working in minutes, without mess, without fuss, without difficulty. Now that being said, wireless networks operate differently than wired networks in a lot of different ways. As the name wireless suggests, it uses radio waves rather than cabled media to create connections. Because of these differences, it's important to know how each operates and how you can best support those types of environments. Let's take a look.
We want to begin with understanding just a couple of basic principles about radio frequency fundamentals. Understanding how radio frequencies work in general is going to help you better understand how wireless LANs, for example, operate. Now, there are several aspects of radio frequencies in the wave, such as what you see here. You have a waveform and you have some length of time. The first aspect of understanding RF signaling is what's called amplitude. You can actually see by the red line that's here, it's actually showing the power of the particular signal. And so amplitude is the strength of an RF signal measured in either milliwatts, MW, or decibels per milliwatt, dBm. Next you have a frequency, and frequency is 1 divided by the measure of time. In essence, it's how often a signal repeats itself within a specified time frame. You're familiar with frequencies because if you've done anything with radios, for instance, you're listening to a song or sports talk or something like that, you're actually tuning to a specific frequency. And then there's finally something called phase. Phase is you have some sort of a reference point and you're actually measuring how the signal differs from that reference point. It can be time, it can be another waveform, and so forth. So typically the three things you need to keep in mind with radio frequency, regardless of the technology involved, are amplitude, frequency, and phase. Now, because radio frequencies actually use the air, which no one really controls per se, there are some different factors that can actually affect the way RF signals work. And so it's important to understand what those are. The first is objects in the path. It can actually be something unfavorable for radio signals. You can have absorption, reflection, refraction, scattering, and so forth. Actually takes the signal and either bends it or scatters it or degrades its power. So many times, for instance, within an office, you might actually have metal filing cabinets, walls, cubicles that can actually degrade the quality of the signal. You also have what's called attenuation or loss. The farther a signal travels, the weaker it gets. It works the same way with wired networks as well. So there's going to be a corresponding, for instance, drop in speed the further away that it goes. And then you're just going to have plain old-fashioned interference because you can have other radios actually competing for the space. You can have microwaves, you can have cordless phones, you can have Bluetooth, you can have other wireless access points, for example, but all these can actually affect how well the signal is propagated or compromised. Now, there are several different types of wireless technologies that you're going to encounter, and we just want to summarize some of those now. For instance, there's infrared. You don't actually see infrared because it's outside the visible light spectrum, but there are infrared printers. I actually owned a laptop one time that had an infrared port, and it's one way you can actually wirelessly connect something. Of course, there's Bluetooth, headsets, smartphones. There's a variety of different types of devices that use Bluetooth. And then you have what's called the 802.11, sometimes collectively referred to as Wi-Fi, which is obviously wireless LANs that are used for data. So these are just some of the different types of wireless technologies that you're going to encounter. Now, Wi-Fi networks use airwaves to connect devices to a wireless local area network. And so it's important to understand how this fits together. So you have personal computer of some sort. It could be a laptop, it could be a desktop. There's some sort of device called a transceiver. It's a transmitter and receiver. So one device might be transmitting, the other device might be receiving, and so forth. whatever radio card is being used, sometimes called a client adapter, it's actually going to have either an internal or external antenna. And it uses that to be able to transmit an RF signal across the medium, which is essentially the air. And usually there's some sort of wireless access point that's frequently used to be able to serve as sort of a go-between to coordinate these different signals. So this just gives you an idea of some of the basics of radio frequency technology. Just as wired networks have certain standards for operation set by standards bodies such as the IEEE, so wireless networks also have certain standards you need to be aware of. When wireless was first introduced, the 802.11 working group of the IEEE actually released the 802.11 standard. This is the legacy or original standard. It talked about 20 to 22 megahertz channels and 3 non-overlapping channels. Now you have 1 through 14 represented here, and this is going to differ depending on the country you're operating in. In North America, typically 1, 6, and 11 are your non-overlapping channels. And there were 2 types of technology that were being used. One was called direct sequence spread spectrum, and just basically spread spectrum takes radio power and spreads it out over a number of frequencies so it can coexist with other media. And then there was also frequency hopping spread spectrum, which would actually hop around to different frequencies using a specified pattern for transmitting data. Typically for this, in the 2.4 gigahertz range, you were going to max out at about 1 to 2 megabits per second depending on the technology used. Fairly slow by modern standards, and it's now considered obsolete. You're not going to run into, in general, any 802.11 original standard devices. The 802.11b standard was really the game changer, which actually made wireless experience widespread adoption. It was relatively inexpensive. You had 11 megabits per second that were available, and there were just a lot of great things that happened with 802.11b. Same basic framework, same channel width, same 2.4 gigahertz range, but it used direct sequence spread spectrum, and it actually had a standard of up to 11 megabits per second, which was very, very fast compared to the original 802.11 standard. Now, at the same time, the 802.11a standard was released, which actually used the 5 gigahertz range. It actually had many more channels. It uses what's called orthogonal frequency division multiplexing type of technology, and it supported rates up to 54 megabits per second. The thing is, 802.11a was more expensive and it didn't really catch on. 802.11b far, far more widely adopted. Then the 802.11g standard was adopted, which actually used either direct sequence spread spectrum for up to 11 megabits per second, or it could use the orthogonal frequency division multiplexing to get the same speeds that were experienced with 802.11a. And the best part about 802.11g is it was backward compatible with 802.11b. 802.11a and b are not compatible. They use different radios, different frequencies, and so forth. And finally, you have the 802.11n standard, which uses both the 5 gigahertz range and the 2.4 gigahertz range using orthogonal frequency division multiplexing. And the best part is it's backward compatible with 802.11a, b, and g. It uses a technology called MIMO, or multiple input, multiple output, essentially multiple antennas, and there's a lot of finer details in this that I won't get into now. But it actually allows for speeds of up to 600 megabits per second. So 802.11a, 802.11b, g, and n are all standards you certainly need to be familiar with when dealing with wireless in the 802.11 world. Now that you have a good feel for RF technologies in general and wireless LANs in particular, along with standards, let's talk about wireless LAN components, the devices that actually allow it to operate. And this includes both physical components and logical components. Let's begin with physical components. And the first link in the chain of wireless communication is actually the client adapter, or a client radio. There's actually 2 basic types, internal and external. The external type of client adapter can be USB connected, it can be a PCMCIA type of card, but essentially it's external to the system in some form. In other words, it's not integrated into the motherboard or within the system. The other is internal. For instance, most laptops come with internal wireless adapters that just simply come as part of the system. In fact, the actual antenna assembly usually surrounds the laptop display. The next most important physical component is actually the access point, sometimes called an AP or a WAP, meaning wireless access point. And this is the device that actually sends and receives signals and acts as the rallying point for all client radios. Normally, you don't have client-to-client communication. It actually takes place via an access point. In addition to these physical components, and there are certainly more, but that's actually a good summary of the primary ones, you actually have logical components that enable wireless communication. The first is called the SSID, or Service Set Identifier, and it actually identifies one wireless LAN as opposed to another. You actually see in this screenshot here, this is from a tool by MetaGeek. It's called NSSID, and this is version 2.0, and you can actually see several distinct SSIDs. One is called ATT Wi-Fi, which is usually Starbucks, Open Free, which is actually a local hospital, and then various number of different items here. But the point is, a distinct wireless LAN is identified by the SSID. One of the things that is sometimes used as a security method is to disable the broadcast of the SSID name, in which case you would not actually see it on this diagram. The next logical component has to do with being able to get an IP address. Normally, over the network infrastructure, just as we talked about DHCP and IP version 4 services, a wireless station actually requests DHCP services from a server that's on the same wireless LAN. So it sends out a request, and normally it comes back in the same process we talked about before. However, there are times when you actually send a request and it fails, meaning that the server doesn't actually receive the request, or for some reason the transmission back is blocked. When that happens, you have an automatically assigned address which is in the range of 169.254.0.0 and /16, and we talked a little bit about network types earlier. This is actually sometimes called the Microsoft Windows Auto Configuration address. It's also called an APIPA address, Automatic IP Address. And basically, it's what's assigned to a workstation if for some reason it doesn't receive some sort of DHCP assignment. The last subject we want to cover is actually wireless LAN security. When the 802.11 standard was first introduced, security was very weak and it caused a lot of concern, and there were a number of different breaches that took place. In fact, I actually had a wireless sniffer when wireless was first introduced, and actually noted in a particular business district that actually there were a great number of access points that were not using encryption of any kind. Everything was open, and it could have resulted in a great deal of data loss. So it's something that has become much more robustly addressed, but it is something that you need to have a very keen awareness of when it comes to how to protect wireless networks. To begin with, there's just some simple techniques that you can use. These are not foolproof. They're not really security techniques per se, but they're just some simple things that you can do to actually try to secure a wireless network. The first thing you can do with reference to the SSID, or Service Set Identifier, is actually to disable SSID broadcasts. And what this means is that those who want to associate with that particular access point in wireless LAN have to actually know what the SSID is, the actual string of characters. It's not foolproof. One of the things that can happen is with a wireless sniffer, you can actually get what are called beacon frames coming from the access point, and you can actually still discover what those SSIDs are. So it is far from foolproof. Sometimes it's called SSID cloaking as well. The next method is actually used between the client and the access point. In this case, you're using what's called MAC address filtering. Let's say, for example, this particular workstation that's listed here, let's say it's using the MAC address 001c.1ad6.4012. The access point would be configured to permit traffic from that particular address, but to disallow it from others or from unknown addresses. It can be a bit cumbersome because these all have to be programmed into the access point, but it is one way of being able to add a little extra security to a wireless network. And this actually brings us to actual security standards that were implemented for the 802.11 protocol. The very first one was called WEP, or Wired Equivalent Privacy. By the way, it was not Wired Equivalent Privacy, that was just the name they chose to use. It was the first standard for authentication and encryption for wireless networks. However, it was very, very weak and identified as having limited capabilities. Just some weaknesses with WEP, for example, were that it used private pre-shared keys that were rarely changed. I actually know of a large healthcare facility that used the same WEP key phrases for a long period of time, and one employee that had been gone for a long period of time was able to go back and access the network using those WEP passphrases. That's just an example of a pretty serious security flaw. In addition, it uses a very small key that in fact was cracked in 1994, so it's something that's easily compromised. The payment card industry, PCI standard, forbids the use of WEP anytime you're using payment cards. And there's all sorts of other weaknesses that are associated with this particular protocol. It's better than nothing, but it really doesn't offer much security. The next standard that was introduced actually came from Cisco on the Wi-Fi Alliance. They actually created an interim solution while waiting for the WPA standard to be completed. WPA ended up being defined by the Wi-Fi Alliance in 2003 and was designed to replace WEP. And there were two types. There was WPA Personal, sometimes called PS Key, which stands for Pre-Shared Key, and then there was the Enterprise 802.11 WPA standard. And this used 802.1x, or the Extensible Authentication Protocol. And WPA uses dynamic encryption keys that change each time a client associates or authenticates with the access point. So there's a lot of other aspects, but WPA was a much greater stride in wireless security. Next, and most current standard, is what is called WPA2, or 802.11i. Basically, 802.11i is the IEEE designation, provides much stronger encryption and authentication methods. Now, it's not backward compatible with any of the other methods. It actually has greater key length and actually uses AES for encryption, and that stands for Advanced Encryption Standard, and is considered to be the most secure encryption method that's available. So 802.11i. So if you have a choice, always use WPA2. As a fallback, you might use WPA, but never, ever, ever use WEP. And we talked at length about the different parts and technologies used with wireless networks. We actually want to take a little bit of a closer look at that now using this particular laptop we're a part of. To begin with, this is actually the list of available SSIDs that are a part of the area that this particular wireless adapter is able to receive and hear. Notice here we're actually connected. You can actually look at the properties. And this shows you a little bit about the network itself. First, the SSID, as we talked about, the type of network, and what's available. And here, there's really no authentication or encryption. We talked about wireless encryption. So this is just some basic information. But the tool we actually showed you is actually in SSID, and it actually shows you different types of wireless networks that are available for scanning. Here we're actually bringing it up now. We'll not upgrade right this minute, but we want to start scanning. Wow, all sorts of things immediately available. Obviously, we have the public library that we're already connected to, but there's so many other SSIDs that we can actually look at, and all sorts of information. And it talks about the vendor that's being used, the specific SSID. Notice this one's blank and this one's blank. This means that its SSID is not being broadcast. The rate that's available, and then if you actually had a GPS connected, you'd be able to see this. This is actually a freeware type of tool that you can actually get from metageek.com. And if you actually were looking at the 5 gigahertz channels, if we had that capability, this would be something else that we'd be able to do. So again, just a brief look at some of the tools that you can actually work with in terms of wireless network connectivity. So just some terms to be familiar with as we summarize this lesson. The first is amplitude. And remember, this is the strength of an RF signal measured in either milliwatts, MW, or decibels per milliwatt, dBm. SSID, or Service Set Identifier, this is an alphanumeric string transmitted by access points to identify a specific wireless LAN, and client radios associate with that SSID. The other two terms are actually related to security. You have WEP, Wired Equivalent Privacy. Now remember, this is the original 802.11 protocol for authentication and encryption, which was weak at best and should not be used. And then you have WPA2, also referred to as the IEEE standard 802.11i, and this is the latest security standard for authentication, both personal and enterprise, and also with encryption.
Now, as a result of the lesson we just completed, you could obviously have a pretty good grasp of how wired and wireless networks differ and what the support requirements are, obviously, for wireless. Wireless as a technology has an incredible amount of detail, far more than we were able to cover in this particular lesson, but you could certainly pursue this in other courses. It's one of the great benefits of a company like TrainSignal. We cover a variety of different technologies, certification paths, and things that you can use for professional development. That's all we'll say about wireless for now. We'll have more to look at in the A+ course in just a little bit.